So in this video, we'll consider this interesting limit and see what we can do about it. So when we look at this, we see that trying to take the ratio test is probably not going to lead to anything useful, and the brute test as well. So we need to kind of develop this expression, play sort of way in a way with it, and maybe reorganize it. So that's what we'll try to do. So first of all, we have this natural logarithm of when we have this n square root, this is like this to the power of 1 over n. So this 1 over n can descend over here, and then we have here 2n factorial over n factorial. Okay, so this is it, and then we have this minus the natural logarithm. So we'll now try to develop this expression, and then eventually we'll bring the limit over here. So now if we look at this 2n factorial over the n factorial, then, well, we can reduce things here, because 2n factorial is the product of all the numbers from 1, then up to n here, and then from n up to 2n by steps of 1. So here eventually we'll reach 2n. And when we divide by n factorial over here, then n factorial, this is exactly n factorial, so this all reduces with this. And so we can write this as a product. So we'll write it as a product of n plus k, and here k goes from 1 to n. So that's our product. And when we plug it inside, so what we have for this expression, this all equals to 1 over n, and here we will have the natural logarithm of the product of over k, where k goes from 1 to n, and here we have n plus k. Okay, minus natural logarithm of n, and though it may seem that we are not making any progress, we are. So now the property of the natural logarithm, or of logarithms in general, that the logarithm of the product is actually the sum. So we can write it in the following way. So we have 1 over n here, and then here we're going to have the sum of n plus k here, and again k goes from 1 to n. And here from all this expression, we need to subtract logarithm, natural logarithm of n. Now we can see that if we were to write this natural logarithm of n, which is a constant for this sum, because this is the sum over k, and we push it actually inside here, then this is the same expression, because here we actually sum n times over the constant natural logarithm of n, and then we divide by 1 over n, and therefore we arrive at the same expression. And now finally, if we use this another law of logarithms, that the difference of logs is actually the log of the quotient, then we arrive at the following sum. So this is 1 plus k over n here, and here times 1 over n, and here we have the sum over k that goes from 1 to n. Okay, so this is, we're almost done. So now we need to make another observation, and to see that actually this is like sum, or like a Riemann sum of some function. So if we were to consider the function f of x, say natural logarithm of 1 plus x, there are other choices, like it depends on the interval. So we'll consider it on the interval from 0 to 1 here. And then what we can see, that this sum over here is actually the Riemann sum. So if we take a partition of this interval into equal n parts, yeah, and let's plot just the sketch of the graph. So here it's going to be the natural logarithm of 2. And if we plot the sketch of this graph, this is approximately how it goes. Then we see here that in this sum, so a point like this endpoint of an interval is going to be k over n. That's our sample point. Here we're going to evaluate the value of the function, and the width of this interval is actually 1 over n, because they're all of the same size. So this is 1 over n here. And so basically what we have here is, this is actually a Riemann sum of the form. This is the sum of the form sum of f of psi I times delta xi, and where I goes, say, from 1 to n. And so this is a typical Riemann sum when we take a function and we partition it to intervals delta xi such that the maximum length of the intervals tends to 0. Then for every choice of the points in the interval, for every choice we will the sum will tend to the same limit as n goes to infinity when the function is Riemann integrable. Now this function is continuous, and so every continuous function, there's a theorem that says that it is in particular Riemann integrable. So and yeah, we know it from, because when we start from k equals 1, we actually choose this side over here. And so in fact this sum is an approximation of the area beneath the graph of the function by this type of rectangles, as you can see over here. So it's actually an upper box sum, but anyway, here the intervals as n goes to infinity tend to 0, and therefore for any choice of the points, in particularly for this choice we're getting the upper sums, it tends to the same limit, and the limit, of course, so let me write it this way. So now our original limit is the limit as n goes to infinity, and here we have this summation, the k's go from 1 to n, and here we will have the natural logarithm of 1 plus k over n, and all of these times 1 over n. So this limit is going to be, since natural logarithm of 1 plus x is a Riemann integrable function, then this limit is going to be exactly this integral. And then we can compute this Riemann's integral by relying on the fundamental theorem of calculus, by just computing the antiderivative of this function with integration by parts, and then substituting the edges, the endpoints here. So, and we can think of it as being 1 times the natural logarithm of x. So we'll compute it by parts, and in the next step we would like to differentiate this function. So we will choose this as u, and this we'll choose as v prime. So our integral is going to be u times v, so v is x, and then natural logarithm of 1 plus x. And here we need to evaluate at the endpoints, so which is from 0 to 1, and then minus the integral, and here v is x, and the derivative of u is 1 plus x, and from 0 to 1 dx. Okay, so as we can see, the first part, so at the 0 it is 0, so when we substitute 1, we're getting the natural logarithm of 2 over here, and here we can write this integral, so minus the integral. Here we can write this as 1 minus 1 plus 1 over x, and all of this dx from 0 to 1. And well, the integral of 1 is obviously going to be 1, so this is natural logarithm of 2, and here minus 1, and then we have plus the integral, because minus minus, so it is plus, plus we're going to have the integral of this, but the integral of this is actually again natural logarithm of 1 plus x. And so here, when we compute it from 0 to 1, then this gives again natural logarithm of 2, and so our answer is twice the natural logarithm of 2 minus 1. This is our limit. So thank you for watching, and I hope that you enjoyed it.